Thank you everyone for joining me today. And in my presentation, where I'll be talking about securing the connected car and some of the challenges that are ahead of us or in the automotive industry. So just quickly, what we are seeing a rough history of cars and software that you have in the car. And we are now moving to an age where the car very much is the software-defined car, because we are pushing more and more software into our cars. But if you go back a bit, in the 90s, you already basically had hardware and electronics in the car. Then you started introducing telematics, which is basically sending information about the car to the cloud, or to be able to diagnose or to monitor usage behavior and so on. And then we started introducing things like infotainment, which is in-vehicle or infotainment or in-vehicle infotainment, which is usually a dashboard in the car which controls the radio, AC, and you can connect your Bluetooth phone, and so on. We also saw more connectivity, so the cars so it's an evolution of the telematics in the cars. So the cars got more connected, more data is able to be read from the car and sent up to the cloud, so to say. And now we are seeing a lot of features like assisted driving, which requires also connectivity and the data. And autonomous drive is something that every company is working on, and there is a big race in even not traditional car companies like Apple or Uber are also working on autonomous vehicles. So it's a very big effort now but all this means is, it's software that's running in the car. But just quickly about me before we move on. My name is Mirza. I've primarily worked in embedded Linux market during my career. I do have a background in automotive, mostly because I live in Gothenburg in Sweden, and it's kind of hard to avoid automotive since we have Volvo and Volvo Trucks and all of those companies are there. So in some way or another, you're working for automotive in Gothenburg. And I've been mainly working with something I like to refer to as board support package development. So it's usually some kind of product running Linux and getting Linux running on a hardware, basically. And I've also always been interested in open source software. And that is why I today work at a project called Mender.io, which is an open source project for doing over-the-air updates on Linux. And of course, there will be an angle to the presentation where software updates is shown to be quite crucial moving forward in this industry. And during this session, we will talk a bit about the opportunities that we are seeing by introducing more software in the cars. This brings value to users and drivers. We will also take a look at anatomy of an attack, so security risks of the connected car. By introducing more software, we're also introducing more ways in to the cars. And specifically, we'll take a look at, in 2015, there was a famous hack done on the Jeep Cherokee. It got a lot of media attention, but a lot of people don't know the details, how it was done. But we will take a look a bit on that and hopefully learn something from that. Then we will also take a look at the patching problem and solutions designs on remedying security problems in cars. So good so far? Yeah. The driving force of adding more software to the cars is, of course, that companies see new revenue streams by offering more services in a car. So you sell a car, and then you can offer subscription services that obviously you can make more money out of it. And it's usually the driving factor of most things is money. And there's been some research that says that automakers could make up to 27 billion annually from services alone, additionally to selling the actual car. And a good example of this is Tesla, who has been doing this for a while now. They usually sell the cars with all the hardware attached to it, but then you cannot buy additional features, which you can enable either during production, but you can also buy them later on. And one of them is the autopilot, which is a semi-autonomous driver. And this feature you can buy like years after you bought the car. You can contact Tesla, and then they deploy a software update and enable that feature for you. So the hardware and the sensors is all there from the beginning, but it's like an additional service that you can buy, and it's software. So there's a lot of like building these infotainment or in-vehicle infotainment systems can typically be described like this in the stack of the software. You have some hardware at the bottom. You need some board support package, operating system, over there updated middleware. And this is usually where most of the cost of developing is, these lower layers. So what we are seeing is that there is a move to more and more to try to use open source components for the lower layers, because in the end, the differentiation between different brands is in the upper layers. It's in the applications that we provide, or the human interface. That's where you can differentiate. The user doesn't really need to know, or doesn't really care what kind of operating system you have underneath. So lately there's been quite a large focus on trying to use open source components in the lower layers. And I don't know if you're familiar. For example, there is a automotive grade Linux, which is a pretty big project, which is basically a collaboration between a lot of companies. So like Toyota and Honda, and there's a lot of car brands involved that are sponsoring this project. And that's basically to create a baseline OS that they can collaborate on, instead of all of them trying to create their own for each new generation of cars. And then just focus on the application level and user interface to differentiate from between the brands. And obviously they want to using open source here, they can shorten time to market, lower the cost, and reallocate development. But taking a look at this stack of software, and anyone that works with software will know that software is not perfect and it needs to be fixed, which essentially means that cars will require over-the-air updates when you introduce these kind of capabilities in a car. And there's been some research that 33% of current recalls of cars could probably have been fixed using OTA. So there is a lot of money to save here. Recalls are costly, so that means you need to inform the user to drive the car to a shop and maybe plug it into a computer and update the firmware on-site locally. So there is a lot of initiative to provide over-the-air software updates to save money, basically. And there's also been some research on that, and according to this research, there's a lot of money to be saved. And this Fiat Chrysler hack that I'm going to talk about, what they ended up doing is they had to recall 1.4 million vehicles. And this was something that if they had over-the-air capabilities, they could have fixed it. So there was a lot of money to save here. So I want to talk about this Jeep Cherokee hack. So it was presented by 2 researchers at Black Hat in the USA in 2015. And they had been working for approximately, I think, around 2 years on this. But in the end, what they could do is, through the cellular network, take control of the car. And this is quite easy to find. There's videos where they demonstrate this, where they basically take control of the car. And taking control means they could brake, they could steer, they could accelerate, they could essentially do anything, and doing it over cellular network. That's so they could basically control any car. And there was obviously like a physical risk to this. If someone is to exploit this, they can harm someone using this. And that resulted in 1.4 million cars being recalled, since they had no way to fix it remotely. I know, and in some cases, I think they sent out USB flash drives to people as well, so they could like update from software in it. So what I wanted to do is just go through this, because the researchers published after a while, once they had fixed this, they published everything. So the software they used and what process they went through to actually get access to this vehicle. So there's a very extensive documentation on this, and also software, so people could actually reproduce this. But hopefully they have fixed it. So just a simple overview. So the Jeep Cherokee had an in-vehicle infotainment unit, which is shown at the picture here. So this is the unit that controls the radio and AC and stuff like that. And what they found interesting is that this head unit was connected to 2 internal networks. So for those who are not familiar, controller area network is an interface that's used in cars to communicate between computers. And this specific car had 2 networks, and they were both connected to the head unit. So in theory, if they could exploit the head unit, they would have full access to the car's ECUs. So, and ECU stands for electrical computer unit. Control unit, yeah, that's it. Yeah, thank you. And as you can see here, they had 2 different networks. So on this network, they had the radio, AC, and not super critical components. And then they have this different network where you had engine, steering, brakes, which raises like interesting question. Why would you give a computer access to brakes? Does anyone know? Yeah, so it's features like ECUs handle things like adaptive cruise control. So they need to be to control accelerating or deaccelerating, electronic brakes. So if you have a parking assist feature, it needs to be able to steer and like brake and everything. So that's why you give controls. And there are safety measures. So like you cannot steer if you're over a certain speed. But during this research, they actually found that they could get past these security measures as well. So they could do basically anything with the car once they got in. And there's a lot of, in this research paper they published, they went through what they were looking for is a remote way to access the vehicle. And there's a lot of radio in the car nowadays. I mean, you have the key to the car is transmitting radio, so they were looking at maybe you could try to exploit that to get access to the car and so on. But they knew that, I mean, this car had Bluetooth, Wi-Fi, and cellular. And these are well-known. I mean, Bluetooth is quite a huge stack, and it has had known vulnerabilities in the past. The same with Wi-Fi. It's pretty well known a well-known interface. And the cellular is the holy grail of these type of things, because then you have like a global reach of vehicles. I mean, Wi-Fi, if you can exploit Wi-Fi and get access to something, then you have to like physically be near the car. But if you can do it through cellular, then you don't really need to be in the vicinity of the car. So of course this car had Wi-Fi. And this was like an additional service that you could buy when you buy the car, where the car could act as like a hotspot or an access point for Wi-Fi. I mean, I guess the value add for that is if you're like the Jeep Cherokee is a very big car, and it's probably used quite a lot in like professional work or construction workers, and they're maybe traveling around to different sites, and then they maybe want to activate some kind of access point when they are traveling to work while they are moving. So that's at least what I think what the access point is for. And you can also like give it access to tablets and whoever the passenger is and so on. And of course the Wi-Fi was Wi-Fi password protected. But passwords are guessable. So they focused initially on this Wi-Fi-based approach to like get short-range access to a vehicle. And what they did is basically you could download a firmware image. Anyone could do that to update the software of your in-vehicle infotainment system. And this ISO image was not really encrypted or anything, so they could reverse engineer all the binary files to fill and like read the code to try to find. And what they found is that the Wi-Fi password was based on it was changed every time you rebooted the car or restarted the car. The Wi-Fi password was changed, and what they find is that they had some like random generator, that was based on time since epoch. And what they found is like it was not unclear from the beginning where the epoch is, but still if you know that it's based on time in seconds since some point of time, you can brute force it pretty easily. But luckily they also discovered, that during a brief window during startup, the car did not have a valid time, and it always started at January 1st of 2013. And they had it took like 1 minute before it got an actual time either from the GPS or from cellular connectivity. So during this window, they could predict pretty much the password of the Wi-Fi and get access. So once you have access to the Wi-Fi, you can communicate with the access point, which is the in-vehicle system. And then I can not call it an exploit, but they were connected to the Wi-Fi network and then started to, the first thing you do, you check, does this device have any open ports? And what they found, yes, it has 9 open ports. And they found one particular port interesting, which was port 6667, which is normally used for like IRC servers or like internet relay chat servers. So they were like, this is probably not running a IRC server, but they are running something on it. And by simply like telnetting to that port on that device, they could figure out that this is actually a dbus interface exposed over IP. And dbus is everyone familiar with dbus? Pretty much. Just quickly, yeah, it's like inter-process communication and RPC daemon used on Linux. And this was exposed over this IP port. And it allowed anonymous authentication, so it didn't require anything. So for them, it was just to hook up something to inspect what's going on, to find more information about the unit. And they used the dfleet, which is like a common tool you use to debug the bus interface to just get an overview of what's happening and so on. And in the end, it was like 4 lines of Python to get to be able to execute root as root, and they were basically in. But still, I mean, they wanted to continue doing this because they had Wi-Fi access and they could go into the vehicle. But they wanted to research, like, can we do this not using Wi-Fi? I mean, they had full access to the in-vehicle infotainment system now, so they could inspect all the things, what's going on internally. So of course they wanted to try to connect to it using cellular network. And the interesting part was this was a combination of maybe unlucky, but they were able to figure out that they are using Sprint, which is a phone provider or like mobile provider in the US. And they could figure out which IP addresses the car got, because the IP address to the mobile network changed every time you restarted the vehicle, but it was always in these particular ranges. And typically on a mobile network, 2 devices connected to the same network are not able to communicate with each other. And this is the mobile provider that's supposed to block this, right? So my mobile phone cannot connect to someone else's mobile phone because we are on the same network. But in this case, on this Sprint network, the case was that you could connect between 2 devices on the same network within that mobile provider. And this was not really their fault, but it's still allowed to. And from there, once they figured that out, it was pretty much just connecting, probing. You were needed to be connected to the same mobile network, so using the Sprint and so on. But then you can just probe for these sub addresses and this specific open port, and they could find vehicles, which is quite amazing. But they still didn't have access to the CAN bus. So they initially thought if they got the control over the in-vehicle infotainment system, they would be able to access the CAN bus, which they were not. So the CAN bus, the in-vehicle infotainment system, was not connected to physically or to be able to control anything, right? So you could only maybe control the AC or change the station. And they figure out there's this chip in between the CAN networks and the head unit. It did allow to read CAN frames, but you could not write CAN frames to the CAN bus. So they started working on. So one thing that the head unit could do, the head unit can update the firmware of this V850 chip. And there was no authentication or verification of signatures or anything. I mean, they had to spend some time developing this, but it was fully possible to flash this chip with a malicious firmware, which gave you full access to the CAN buses. I mean, even if you get full access to a CAN bus, there's a lot of effort figuring out what the decoding protocols and what do the messages mean. But it's all possible if you have full control and you can read what's going on. You can reverse engineer it if you're given time. So putting it all together, the entry point for them was there was one thing, they did figure out a way of jailbreaking the IVI unit as well, or the head unit, using a USB stick. But they kind of abandoned that once they figured out that they could use the Wi-Fi to get in. They didn't need to physically have access to it. But they discovered other ways as well. Yeah.
I didn't get quite what was the cellular breach. One thing was that the provider allowed the direct communication, but how did it actually got onto that channel? Was it completely open?
Yeah.
I mean, I think
No, but you needed to be like, you take your laptop and connect to the same mobile network.
So it was completely open?
Yeah,
Nothing.
the port was open, so they just had to probe, just try until they found an open device. So they utilized the Wi-Fi hotspot to get in, and then they could learn a lot more about the system. Remotely accessible services in head unit was vulnerable. The firmware update of the extra chip, there was no authentication checks or verification that the software is trusted or provided by a trusted source. And once this was published, there was no way for them to fix this, and they had to do like a recall of all the vehicles to avoid quite serious effects. And this is coming back to this software-defined car. I mean, if you're adding software, a lot of different components, the complexity increases. That's pretty obvious. And I mean, it's no easy task to develop a car. I mean, nowadays you probably have hundreds of ECUs in a car. And these ECUs are probably not developed by the same company, but each ECU is developed by a different company. So there's a lot of moving parts in developing such a vehicle. So maybe the auto manufacturers don't always have the control or don't even know about these problems until two researchers sit down and just... so one cannot really blame anyone here, but it's still amazing that this can happen. And there's been some research that, like, assuming that all software components have vulnerabilities, and like there will be bugs in software. There's no getting around that. One workaround is relying on well-maintained software and keeping it up to date. So that's one way of remedying vulnerabilities in the vehicle. And there is this discussions always, like, is open source more secure than proprietary? Because open source, anyone can inspect it and find vulnerabilities, but at the same time, they can also fix the vulnerabilities if someone inspects it. But it doesn't really bring much to this discussion, I think. And there was some basic, like, security principles that were not implemented in this, like principle of least privilege. And principle of or separation of privilege, to only give access to parts that you need. In this case, the IVI through this chip could access every ECU in the vehicle. It probably didn't have to do this, but maybe it was easier to design it in such a way. And there's also this Kirchhoff's principle, which is a term used in cryptography, which is basically don't try to do security by obfuscation. Do your security work based on that everything is known and so on. And this is a typical example where probably there was, I mean, security by obfuscation, someone can figure it out if just given time and access. Any questions or any comments? Sure.
Actually, going back to the very beginning, the slide with hardware, the drivers, and maybe up to the application layer, you said that the operating system, that there are some initiatives to run the Linux, embedded Linux for automotive grade. And I guess you know that there are those hypervisors commonly used, like Greenhill's, the QNX. How does this really fit into that landscape? Like this automotive grade Linux, would that be running on top of the hypervisor?
Yeah.
Or will it actually replace the hypervisor?
No, it typically runs on the hypervisor. So you would run it in the hypervisor.
You said that it was not possible to patch this remotely. So wouldn't it be possible for the manufacturer to use the same kind of attack vector to replace it?
Probably they could have done that, but I don't know actually. Kind of, yeah. Maybe they were too proud to do it.
How would you do it securely? The car needs to be turned on, but it cannot be driven because firmware is being flashed.
Mm.
So you want the hardware that you have to start the car but not drive it. And that has to continue for a considerable amount of time because the image needs to be downloaded. So how would you force push that hack? The researchers didn't have it. They didn't care about modem customers because they had a targeted car. They could run it forever.
Yeah, and since they didn't have like OTA capabilities, the system probably was not designed to, and they would probably be risking to brick it if interrupted, because you could update it using a USB flash drive, but then you need to like enter bootloader mode and so on. So you could always come back if something was wrong. You can retry it. And there's also been like research on security patching and the probability of exploits. So I mean, it's not uncommon that nowadays that you read about it in the media, exploit here, and so on. And if you patch within 5 to 10 days, there's very little probability that the exploit was exploited. But as time goes by, you increase the chances of someone taking, using a known exploit to get access to something. So why does security patching happen so late? Typically the value is invisible until it's too late. So you don't really think about it until something like this happens. And then you're kind of reminded, oh, we should have done something earlier. So there's a lot of, I think there's a lot of this mindset that, it doesn't provide any value until someone breaks into your system and does something. But you need to be forward thinking about that. Too costly or too risky, this is a bit what you're talking about here. If you don't have like a OTA updater, you would risk breaking the vehicle of doing an update. So that's kind of why you don't do patching. Do you have any ideas, like why would, any other reasons why you don't patch in time, or why it does take so long time? Is it something that you think about in your products, like try to monitor? Do you have a schedule? Yeah. But yeah, patching connected devices is not an easy feat. So it's not. You probably assume then that you don't have a physical access. So if something goes wrong, you cannot fix it. So you need to be prepared for every possible failure and be able to recover from that. And that's why you need failure management. Vehicle is a very good example of unreliable power. Someone can turn off the car at any point. Some ECUs keep running even when you turn it off, but you don't really know. Maybe they disconnect the battery, and so you can never be sure that you have reliable power. And the car is a perfect example of that. You have unreliable wireless connectivity. And 3G modems and so on. A lot of things can go. You can enter a tunnel, you lose connectivity, so you need this additional and you also want to resume and not restart the download. If you are in the middle of download, you enter a tunnel. You don't want to restart from the beginning. That's wasteful and probably costly. And verify authenticity of update is important, as shown in this example. So this is, I mean, through my daily job, I do a lot of, we focus on over-the-air updates. And this is something that we think about a lot. And we usually show this, and this is like a generic updater, embedded updater workflow. And there are some must-haves here. Some are like environment specifics. But typically, the workflow is you detect an update through a secure channel, not an insecure channel. There's some kind of compatibility check. So this image only works on this device. Then you download the image, the firmware that you want to update, also through a secure channel. There's some basic integrity checks because you are transferring bytes over like wireless connectivity. There is a chance that some bytes did not arrive. Authentication signature, this is to verify that this come from me and not from someone else. And this is a good example of this Jeep thing that had they had such a process in place, they would not be able to replace the firmware or components and such and so on. In some cases, you also encrypt the image. Yep.
Just a question at the end of your explanation.
Yep.
You say that you should do the detecting for an update and downloading of your update on a secure channel.
Yeah.
Can you explain why? As in, what kind of failure would you get if you did this on an insecure channel?
Well, someone can inspect your software, get hold of your image.
Detecting for updates and you get no secure connection, or you get somebody else to tell you there's no update, then nothing happens.
No, not on that particular update, but someone can get access to your image and inspect it and learn things about your system that they can use to later exploit it.
So that would be making sure the download will only happen from a secure device, not necessarily on a secure channel.
No, both.
In the case of the download on a secure channel, if you then do an integrity, authenticity and decryption, what's the point of having secure?
If it's encrypted, there's not much point because secure channel is encryption basically. So.
Yes, there is a point. Because otherwise somebody might force an older software which has no bugs, which has been designed by the manufacturer to be pushed to your car, which is 20 versions behind the car and has no response. And you will have to download it, either substitute it to the unsecure channel from factory to your device. So that would typically be a pre-install action. You don't allow downgrade. You don't do that because if you unfortunately roll out an upgrade which ruins something, you need a way to forcefully downgrade everybody's superpower.
Yeah.
So both the manifest and the download must be over a secure channel, precisely to prevent those kind of problems.
And just you had the slide with the box. I mean, more layers of security. It adds the number of bugs as well, but you have more layers of protection as well. You wouldn't rely on just one layer.
I agree. You need the only way to do this properly is that the device has downgrade protection. And if you have one version which you realize is the problem, the fix is not to play out another version. The fix is to take the version A that you had, if version B was faulty, just rename it as version C and put it back up. That's the fix to it. Because trusting a secure channel, there are, how do you know that they have connected to your servers? The easy thing is to have always have downgrade.
Okay. Let's move on. We can talk about it a bit more later if you come up. I would happily do that. So yeah, decrypt, extract, pre-install, install. Some post-install actions. You probably want some kind of sanity checks. So if you install something, you try it. Does it work? If it doesn't work, go back. And that's what failure or recovery, to be able to roll back to previous if the update failed for some reason. And this was pretty much covered in the workflow. And another example, same company, same in-vehicle infotainment system, why rollback is important, because they pushed an over-the-air, this is a newer version, now they have over-the-air updates. They pushed that over-the-air update, which was broken, and it forced the infotainment system to be stuck in a reboot loop. And it never got out of it, so it basically drained the batteries of the vehicles. And you didn't lose much functionality. You couldn't like control the AC or something. The vehicle still worked and everything, but it was quite annoying for people to. And there was some like missing some kind of sanity check that X number of reboots maybe roll back to the previous version or something. And it took a while to roll out as well. So there are some, like, to summarize everything. There seems to be a move to open source software in this field as well. There are still proprietary solutions, but a lot of companies are trying to rely on this, like embedded Linux or the automotive grade Linux for the next generation of cars. It brings some opportunities. Over-the-air updates, this is going to be like, it's going to exist in all of the future vehicles. And apply well-known security design principles is crucial when you're designing these type of systems. And as one final thing, I just wanted to, so similar things happened, a similar thing happened to Tesla. Someone was able to exploit it using Wi-Fi. And these are like two approaches, how you can react to something like that. So when this happened to Fiat, they were very defensive, and they were like trying to, they called them criminals because they modified their software. And they also mentioned that like you had to have physical access to develop the exploit. But once they did that, they could reuse it on like other vehicles as well. A similar thing happened to Tesla, and they were very like, great, you found a bug, we fix it. And Tesla obviously has over-the-air updates, so it didn't really cost them that much. So it's sort of just different. How you tackle the same problem. And that's me. And any more questions? Okay, thank you.